Hi, welcome back to my class in Algebra. For today, we will study how to solve linear inequalities. But before we do that, we recall the interval notations because in writing the solutions of linear inequalities, we give the solution using interval notations. The first type of interval notation is called the open interval. And the open interval is denoted by this notation, open parenthesis, A, B, close parenthesis. It's like an ordered pair of numbers A and B. And in this notation, the numbers A and B, real numbers A and B, are called the endpoints of the open interval. In diagram, the open interval is represented in the real line. It is a set, the open interval is a set of real numbers between A and B, but the endpoints A and B are not included in the open interval, and we denote that by open circles. Again, the open interval AB, represented diagrammatically in this way, is a set of points between is a set of real numbers between the real numbers A and B, but the real numbers A and B are not included in the set. And we denote the exclusion of A and B from the set by this small circle. The real number A is called the left endpoint, and the real number B is called the right endpoint. The endpoints of the open interval are not included in the set. We also denote diagrammatically the open interval AB in this way. It is a set of real numbers between A and B, but the left endpoint A is not included in the set, denoted by open parentheses. And the right endpoint, the real number B, is not also included in the open interval, denoted by close parentheses. We take three examples of open intervals. This diagram represents an open interval between -1/2 and +1. But -1/2 and +1 are not included in the set, as indicated by these small circles. Hence, this is the open interval between -1/2 and 1. It consists of all real numbers between -1/2 and 1, but the endpoints -1/2 and 1 are not included in the set. And we denote this by the open interval we denote this set of real numbers between -1/2 and 1, excluding -1/2 and 1 by the open interval, open parenthesis, -1/2 and 1 close parenthesis. If the endpoints are not included, we use open or close parenthesis. In number 2, we have this also an open interval, and it is the set of real numbers from +10 and all the real numbers less than 10. And 10 is not included in the set as indicated by this open interval. But the set of real numbers in this interval go up to -infinity, up to the smallest negative real number, and the very small negative real number we denote by -infinity. the set of real numbers from 10 and all the real numbers less than 10 up to the very small negative real number denoted by negative infinity is the open interval from negative infinity to 10. Because negative infinity is not a real number, it is only a symbol that represents a very small real number. Negative infinity is not included in the set as indicated by this open parenthesis. After 10, we have the closed parenthesis because 10 is not included in the set because as indicated by this small circle. So this set of real numbers from 10 and all the real numbers less than 10 is the open interval from negative infinity to positive 10. And 10 is not included in the set. As well as negative infinity because it is not a real number. It is just a symbol representing a very small negative real number. Number 3, this is also an open interval that consists of all real numbers from negative 7 and all the real numbers greater than negative 7. So if the arrow goes from left to right, that means you want the numbers greater than a certain real number. If the arrow goes from 10 to the left, that means the set consists of all real numbers less than 10. If the arrow goes from negative 7 and to the right of negative 7, you want the set contains all the real numbers greater than negative 7. And when you write the interval, you always start from the left endpoint. You do not write the set of real numbers between negative 1/2 and 1 as the open interval 1, negative 1/2. You always start from the left endpoint going to the right endpoint. As in number 2, we started from the negative infinity going to the left endpoint. So if we want to write this in set of real numbers in interval notation, we start from the left endpoint. And the left endpoint is negative 7. But negative 7 is not included in the set because there is a small circle at negative 7. That means negative 7 is excluded from the set, and we indicate that by open parenthesis. And the set consists of all real numbers from negative 7 up to the largest, the very big positive real number, which we denote by positive infinity. Hence, the set of real numbers from negative 7 and all the real negative 7 and all the real numbers greater than negative 7 is represented by the open interval from negative 7 up to positive infinity. And because positive infinity is not actually a real number, it is only a symbol representing a very large positive real number, we write close parenthesis, which means that positive infinity is not included in the set. The second type of open interval is, the second type of interval is closed interval. The closed interval is denoted by this notation. We have now a pair of brackets, A and B. This is the closed interval A and B. And the brackets indicate that the endpoints, the left endpoint A and the right endpoint B, are now included in the set. If you have a closed interval, then the closed interval AB, that's the set of all real numbers between A and B, and the real numbers A and B are also included in the set. And that is indicated by the closed bracket. Geometrically or diagrammatically, we represent the closed interval in this way. We locate the real numbers A and B in the real line, denoted the set of real numbers denoted by capital R. Suppose these are the real numbers A and B. The closed interval is the set of real numbers from A to B, including A, which we indicate by open bracket, and including B, or the right endpoint, which we indicate by the closed bracket. This is the diagrammatic representation of the closed interval AB. In some other books, the closed interval is represented also in this way. The closed interval AB is the set of real numbers from A to B, and the real number A is included in the set as indicated by this bracket. In the diagram, we indicate that by shaded circle, by a dot or shaded small circle. And also the right endpoint B is included in the set, or in the in the closed interval as indicated by this bracket, and we can also indicate that using a shaded small circle. Thus, to represent a closed interval diagrammatically, you may use this representation or this representation. And to represent an open interval diagrammatically, you may use this representation, a pair of braces at endpoints, or open circles at endpoints. We take an example of closed intervals. The closed interval -1, 2 is the set of real numbers from -1 to 2, and the endpoints -1 and 2 are included in the set. We represent that diagrammatically in the real line. And we locate -1 and 2. Suppose this is 0. -1 and 2. The closed interval -1 and 2 is the set of real numbers from -1 to 2. And -1 is included in the set, and we indicate that in the diagram by shaded small circle. And 2, the right endpoint, is also included in the set, and in the diagram we represent that, we indicate that by shaded small circle. In number 2, we are given a diagram, and we write the set of numbers in this diagram using interval notation. You can see that in this diagram, we have a set of real numbers from -3 to +1/3. And because at -3 we have a shaded small circle, that means that -3 is included in the set. And also at 1/3 we have a shaded small circle, and that means that 1/3 is also included in the set. Therefore, we represent this in interval notation using closed interval. This diagram represents the closed interval from -3 to 1/3. This diagram represents the set of real numbers from -3 to 1/3, and the real number -3, or the left endpoint, is included. In the interval notation, we indicate that by a bracket. The right endpoint, or 1/3, is also included in the set because of this shaded small circle. In interval notation, we indicate that by a bracket. Hence, this set of real numbers represented in this diagram is represented in interval notation, in this closed interval notation. Another example, this is the third example. of a closed interval, we have a set of real numbers from 0 to 4. And because there are shaded circles at these real numbers 0 and 4, that means the real numbers 0 and 4 are included in the set. The endpoints 0 and 4, in particular the left endpoint and the right endpoint, are included in the set. And using interval notation, we write the set of real numbers as the set of real numbers from 0 to 4. This is the set of real numbers from 0 to 4, but because we have a shaded circle at 0, that means 0 is included in the set. And to indicate that, we use this bracket. We also have a shaded circle at 4, that means the real number 4 is also a member or element of the set. And in interval notation, we indicate that by this closed bracket. Now we take the last type of interval notation, the half-open intervals. The last type of interval notation is the half-open interval. And there are two types of half-open interval. The half open to the right and the half open to the left. The half open to the left is denoted by this notation, AB. This is half open to the left because the left endpoint is not included. So this interval notation is open at the left, which means that the left endpoint or the real number A is not included. And the right endpoint is included in the set as indicated by this bracket. It's open to the left but closed at the right endpoint. And this interval is called half open to the left. We represent this half open interval in a diagram in a real line. Suppose these are the real numbers A and B. The half open to the left interval, AB is the set of real numbers between A and B. The set of real numbers between A and B, but the real number A or the left endpoint of the interval is not included, and we indicate that by this parenthesis. And the right endpoint B, the real number B, is included in the set, and we indicate that by this bracket. Or another way to represent this half open to the left interval is this way. The half open interval AB is the set of real numbers between A and B. But the real number A is not included in the set as indicated by this parenthesis. In the diagram, we can indicate that by open circle. And the half open to the left is closed at the right endpoint, which means the right endpoint or the real number B is included in the set. And in the diagram, you can indicate that using a shaded small circle. The other type of half open interval is the half open to the right. This interval is denoted by this notation. This notation is the set of real numbers between A and B, but the right endpoint B is not included in the set, and that's indicated by this parenthesis. But the left endpoint A is included in the set as indicated by this bracket. we represent this half open to the right interval in a diagram. Suppose these are the real numbers A and B on the real line, denoted by R, the one-dimensional space. The half open to the right interval is the set of real numbers between A and B. The set of real numbers, all the real numbers between A and B are included in this set of real numbers, the half open to the right interval. The left endpoint or the real number A is included in the set as indicated by this bracket. In the diagram, you may indicate that using the shaded small circle. But because this interval is half open to the right, that means the right endpoint or the real number B is not included in the set. And in the diagram, you can indicate that using the open circle. Or you may use another way to represent this half open to the right interval in this way. This half open to the right interval is the set of real numbers between A and B. But it's open to the right, which means that the right endpoint B is not included in the set, and in the diagram we can indicate that by parentheses. And the left endpoint A is included in the set as indicated by this bracket, and we can do the same. We can indicate that A is included in the set using a bracket. This is the graphical representation of the interval half open to the right, and this is the graphical representation of the interval half open to the left. Now we will take examples of solving linear inequality in one variable. The method for solving linear inequality in one variable is very similar to solving linear equation in one variable. All the properties of equality that we use to solve linear equations in one variable would still apply when solving linear inequalities in one variable. We now take some examples. The difference between solving a linear equation in one variable and solving linear inequality in one variable is that when you arrive at the solution of linear equation in one variable, there is only one value or one solution, one value for the variable in the linear equation in one variable. Whereas when you arrive at the solution of linear inequality, you will find that there is more than one value that will satisfy the given linear inequality in one variable. But the properties of equality and the rules for inequalities apply for solving linear inequality in one variable. And we first recall the rules for the rules that apply for inequalities when you multiply both sides of an inequality by positive real number. The inequality sign remains the same. Again, when you multiply both sides of an inequality by positive real number, the inequality sign remains the same. That's the first rule. The second rule, if you multiply both sides of an inequality by negative real number, the inequality sign is reversed. And number 3, if you add the same constant to both sides of inequality, the inequality sign remains the same. The number 4 rule, if you subtract the same constant from both sides of inequality, the inequality sign remains the same. And number 5, if you divide both sides of inequality by positive non-zero real number, the inequality sign remains the same. Again, if you divide both sides of inequality by positive non-zero real number, the inequality sign remains the same. And lastly, if you divide both sides of inequality by negative real number, the inequality sign is reversed. So the inequality sign will be reversed only when you multiply both sides of inequality by negative real number, or you divide both sides of inequality by negative real number. The inequality sign will be reversed. We now solve the first example. Solve the linear inequality. Show the solution in diagram and give the solution using interval notation. For our first example, the given is 2x minus 3 all over 4 less than equal to 5x plus 4 all over 3 plus 1. This is an example of linear inequality because it contains an inequality sign less than or equal to. And it is a linear inequality in one variable because there is only one variable x, and the highest exponent of x is 1. So the variable x is linear, and we have linear inequality in the given. This is an example of linear inequality in one variable. And when we solve this linear inequality, we will find that there is more than one, actually infinitely many solutions for this linear inequality in x, and we will write the solution using interval notation. The first step, if you have a rational expression in the given, is to eliminate the denominator by multiplying the left-hand side and the right-hand side by the LCD, or the lowest common denominator or least common denominator. Since you only have 4 and 3 in the denominators, if you write the denominator of 1, the denominator of 1 is 1. And the LCD of 4 and 3, even if you include 1, is the lowest number or the smallest number that can be divided by 4 and 3. Again, if you know well your multiplication table, it would be easy for you to think of the smallest number that is divisible, that can be divided exactly by 4 and 3. And that number is 12. That is the smallest number that can be divided. 12 can be divided by 3, 12 can be divided by 4. And to eliminate the denominators, we multiply the left-hand side and the right-hand side by 12. We start with the left-hand side, 12. 12 multiplied by the left-hand side, 2x minus 3. All over 4. We also multiply the right-hand side by 12, multiplied by 5x plus 4 all over 3, plus 1. Since we multiplied both sides by the same positive real number, the inequality sign remains the same. Less than or equal to. Now, 12 is divisible by 4. 12 divided by 4 is 3. And we remove the grouping symbols by using the property of multiplication over addition or subtraction. We multiply each term of this. Now 12 divided by 4 is 3. We can now cancel out 4. We multiply each term of this binomial by 3. 3 multiplied by 2x is 6x. 3, positive 3 multiplied by negative 3. Positive times negative is negative. And 3 times 3 is negative 9. Less than or equal to, we distribute 12. We multiply each of these terms by 12. We start with 12 multiplied by 5x plus 4 all over 3. Plus 12 multiplied by 1 is 12. We further simplify this to remove the grouping symbols. At the left hand side, we still have 6x minus 9 less than or equal to. Now 12 is divisible by 3. 12 divided by 3 is 4. We can now cancel out 12 and 3. 12 divided by 3 is 4. And we multiply each term of this sum or binomial by 4. 4 multiplied by 5x is 20x. Plus 4 multiplied by 4 is 16. Plus 12. Similar to solving linear equations in one variable, you have to collect all the terms with the variable at one side of the equation and all the constant terms, the terms without the variable at the other side of the equation. And we do the same for linear inequalities in one variable. All the terms with x must be collected at one side of the equation, usually the left-hand side. And all the constant terms, those terms that are numbers without the variable x, must be at the other side of the equation. For this example, we transpose 20x to the left and we transpose minus 9 to the right, so that all the constant terms are at the right hand side of the equation. At the left hand side, we have 6x and 20x, that's positive. We transpose to the left hand side. You take the opposite sign of the term, it becomes negative 20x after transposition. At the other side, we have 16 plus 12, that's 28. And minus 9, we transpose to the right hand side. It becomes positive 9. And as I mentioned earlier, if we add and subtract the same constant to both sides of inequality, the inequality sign remains true or the same. Like if we want to transpose, if we want to bring negative 9 to the right hand side, we add positive 9 to the left and positive 9 to the right. And the inequality sign remains true, less than or equal to. But what we did here is we made use of transposition because that's the easier way for most of us. Now, after collecting all the similar terms in one side of the equation, like 6x and minus 20x, these are like terms or similar terms because they have the same literal coefficient x, you combine the similar terms. 6x minus 20x is negative 14x. Less than or equal to 28 plus 9 is 37. Finally, in the solution, the coefficient of x, as in solving linear equation in one variable, must be positive 1. And to make this coefficient of x positive 1, we have to divide both sides of this inequality by negative 14. We divide negative 14x by negative 14. And we also divide the right hand side 37 by negative 14. But because we divided both sides of inequality by negative real number, the inequality sign will be reversed. From less than equal to, it will now be greater than equal to. So you remember, if you multiply or divide both sides of inequality by negative real number, that's the only time that the inequality sign will be reversed. If you multiply both sides by negative or you divide both sides by negative real number, the inequality sign will be reversed. As in this example, from less than equal to greater than equal to, because we divided by negative 14. And negative 14 divided by negative 14 is 1, or simply x. All we cancel out negative 14 and negative 14. And we simply get x at the left hand side greater than equal to is positive, divided by negative is negative. Negative 37 over 14. If we divide 37 by 14, 37 divided by 14 is 2. 2 multiplied by 14 is 28. And 17 minus 8 is 9. And we add 0. 90 divided by 14, that's cannot be 6, 5, 6, 6. 90 divided by 14 is 6. 6 multiplied by 4 is 24. And 6 multiplied by 1 is 6 plus 2 is 8. Okay, we stop at 2.6. Hence, negative 37 over 14 is approximately negative 2.6. This is now the solution of this given linear inequality in one variable. All the values of x are real numbers that are greater than or equal to negative 37 over 14. Negative 37 over 14 is a solution. X equals negative 37 over 14 is a solution. And all the real numbers that are greater than negative 37 over 14. We will now represent this solution. Now you can see that linear inequality has more than one solution. Actually, infinitely many solutions. Unlike in solving linear equations in one variable, you only have one value for the variable in the given linear equation. When you are solving linear inequality in one variable, you will obtain an infinitely many solutions. As in this example, one solution is x equals negative 37 over 14, and all the real numbers that are greater than, as indicated by this greater than inequality sign. All the real numbers greater than negative 37 over 14 are also solutions. We will now represent this in diagram, and we will give the solution in interval notation, and we will also check. We now represent in diagram the solution we obtain, which is x greater than equal to negative 37 over 14, or approximately negative 2.6. This is the solution of the given linear inequality. And we represent the solution in a real line, or the set of real numbers. In the real line or one-dimensional space, you locate negative 37 over 14. That's approximately negative 2.6. Suppose this is negative 2.6 or negative 37 over 14. Our solution says that the solution of this linear inequality in one variable x are those real numbers that are greater than or equal to negative 37 over 14. Greater than or equal to. That means that negative 37 over 14 is one of the solutions, which means that negative 37 over 14 is included in the set of solutions of this linear inequality. And in the diagram, we represent that by shaded circle. All the real numbers greater than negative 37 over 14 are also solutions. And this is negative 37 over 14. The real numbers greater than negative 37 over 14 are the real numbers to the right of negative 37 over 14. Or all the real numbers to the right up to the very, very large positive real number are greater than negative 37 over 14. And thus they are also solutions of the given linear inequality. Our solution is from negative 37 over 14 and all the real numbers greater than. And we indicate that by this arrow. This diagram tells us that the solution of this linear inequality are the real numbers from negative 37 over 14, including negative 37 over 14 as indicated by this shaded circle, and all the real numbers greater than negative 37 over 14 up to positive infinity, the very, very large real number, as indicated by this arrow, as indicated by the direction of this arrow. And we write this using interval notation. When you write the interval notation, you always start with the number from the left, or the left endpoint, negative 37 over 14. After the left endpoint, you write comma, and then you write the right endpoint. For this particular example, the right endpoint is represented by positive infinity. Because as indicated by this arrow, the set of solutions include all the real numbers up to the very, very large positive real number, and the very, very large positive real number is represented by this symbol, positive infinity. Again, positive infinity is not a real number but only a symbol representing a very, very large positive real number. And because it's only a symbol, this positive infinity is not actually part of the set of solutions, and we indicate that by open parenthesis. While negative 37 over 14 is one of the solutions as indicated by this shaded circle, and also as indicated by this equal sign. And in the interval notation, we indicate that by bracket. And this is our solution or our answer in interval notation. And you can see that this interval notation is half open to the right interval, because it's open at the right endpoint at positive infinity. Now we check our solution. You take to check whether you have the right solution or the right interval for your set of solutions. You take any real number between negative 37 and any real number greater than negative 37 over 14. And to simplify, I will take 0. And when x is 0, you substitute x is 0 in the given linear inequality, and you check if the inequality will be satisfied. You replace x with 0 at the left hand side. We have 2 multiplied by x. X is 0. Minus 3 all over 4. And we want to check if that would be less than or equal to. Since we are still checking, we write a question mark above the inequality sign. At the right hand side, we also replace x with 0. 5 multiplied by 0 plus 4 all over 3. And plus 1. Now we simplify each side of the inequality. 2 multiplied by 0 is 0. 0 minus 3 is minus 3 over 4. And we want to know if this is less than or equal to. At the right hand side, we have 5 multiplied by 0 is 0. 0 plus 4 is 4 over 3. Now you can already see that the inequality sign is satisfied. The inequality sign less than or equal to is satisfied, because you can clearly see from here that the left hand side is negative, while the sum of 4/3 plus 1 and 1 is positive. And a negative real number is less than or equal to positive real number. Hence, when x is 0, the inequality sign is satisfied. And you may take other values of x as long as those values of x are in this half open interval, or between negative 37 over 14 up to positive infinity. Take any real number from negative 37 over 14, including negative 37 over 14, and you substitute that in the given linear inequality, and you check if the inequality sign will be satisfied. But this one value of x would suffice, would be enough to tell us that we must have obtained the correct solution. For your practice, please try the following exercises. So, as what I had done in our example, for these exercises, you solve each linear inequality in one variable, and then you represent the solution in a diagram. In the real line, you represent the solution, and then you write the solution in interval notation. In number 1, the given is 3x plus 2 greater than 5x minus 1. In number 2, the given is 6x over 5 plus 1/2 less than x over 5. For you to be able to check your answers, I give you the answer in interval notation, or I give you the solution using interval notation. For number 1, the solution is the open interval, negative infinity, 3 over 2. For number 2, the solution is also an open interval from negative infinity to negative 5 over 11. Number 3, the given inequality is 5 minus 2 times quantity x minus 1 less than equal to 6x plus 2. In number 2, you have to first eliminate the denominators by multiplying the right hand side and the left hand side by the LCD, the lowest common denominator, 5, 2, and 10. For number 3, you have to first eliminate the grouping symbols by applying the distributive property of multiplication over addition or subtraction. And for number 3, the solution in interval notation is this half open to the right interval. The solution is from 5 over 8 to positive infinity, including 5 over 8. In number 4, the given is 7x over 3 all over 3 greater than equal to 1 over 4 minus x minus 5 all over 6. Similar to number 2, you have to first eliminate the denominators in number 4 by multiplying the left-hand side and the right-hand side of the inequality by the LCD, lowest common denominator, for 3, 4, and 6. And the solution for number 4 using interval notation is given by this half open to the right interval. The solution consists of all those values of x from 5 over 6 and greater than 5 over 6. And 5 over 6 is one of the solution. You also check your solutions by taking any real number in these intervals and substituting that real number in the given inequality. And that completes our lesson for today, and we will have more examples for solving linear inequalities in one variable. And in the next examples, we will consider cases, problems with cases, and the solution for these linear inequalities that result to two different cases, two or more cases would be the union of the solutions of the cases considered. If you have a question about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Calizon, the channel of learning and leisure. Or you may ask your friends and classmates to subscribe to my YouTube channel so they may learn as well. Thank you for joining me in my class today.